All right, hello and welcome to these slides again, recursion and beauty. So we're going to definitely finish them up this week. Let's go down to where we were. We were starting with recursion, which is noticing how some problems are inside of themselves. There are smaller versions of the same problem inside of the bigger one. Okay, so we noticed that specifically for factorial, we could see that, if I use a different color so that it's not all blending together, we saw that for 5 factorial, if we wrote it out, we noticed that there are smaller factorials inside of 5 factorial, okay? And usually with recursion, we're looking for the next smallest thing, so the biggest smaller thing, if that makes sense. And we noticed that we can just pull this out, and now we have a general way of solving a factorial. 5 factorial is just, well, you take that number there, you plop it right there, and then you subtract 1, plop it right there, and put a factorial sign at the end. Okay? That was the general idea, and we can, of course, therefore generalize it to say, okay, n factorial, give me any n that isn't 1. We notice we need to stop eventually. Give me any n that isn't 1, anything that's bigger, and n factorial is just, okay, following this pattern, n times n minus 1 factorial. Okay? That's the beauty. And eventually we're going to need to stop, so we have a base case where we know that 1 factorial, once we get there, we immediately know the answer. We don't have to say factorial anymore. We just say, oh, the answer is 1. Cool. All right, so that is the recursive way of solving factorial in a nutshell. And last time we came up with the actual code to go and do that, right? We made a function, def fact, and we just translated all this stuff, right? So he said, okay, if the number's 1, then we know we're in the base case. And the answer that we should give back to whoever asked us for the factorial of 1 is just 1 itself. So we'll return that, and they can do with that whatever they want. And otherwise, if n was not 1, hopefully it's bigger, we are in the recursive case. And so we know that our factorial should be ourselves, our n, times the factorial n minus 1 factorial. Yeah? So how do we get that? We call our own function, because this function is supposed to compute the factorial. You see that? We kind of trust ourselves to handle the smaller problem. Okay? And so call that x, n times x. That's n times n minus 1 factorial, because this returns n minus 1 factorial. Okay? And the beauty or magic of recursion is that you can make this kind of assumption. You can be like, okay, I'm just going to assume that the smaller recursive call to this function actually works. It does the right thing. Okay? And I'm going to try and prove to you why this is going to work. Okay? So first of all, let's program this for real this time. I've made a new file called recursion.py for today's lecture. We will be in it a little bit. So let's first make this function, def fact n. So we're computing the factorial of a number n, and we may be either in the base case or the recursive case. If we're in the base case, we immediately know the answer. If n is 1, return 1. That is the answer. Okay? Otherwise, we know that we're in the recursive case. We need to call ourselves on a smaller version of the factorial problem. We just kind of shove off that work to somebody else, to another version of ourselves. That's the idea. So x equals fact n minus 1. So we call ourselves, get the factorial of n minus 1, and then our final answer is, it's always n times n minus 1 factorial, right? And n minus 1 factorial is sitting in x, okay? That's the idea. And so we'll return n times x as our answer, okay? So that's the complete function, and it's going to work, as long as you don't give it 0 or something smaller. It's totally going to work. So let's say print fact 5, and let me prove to you that this gives back the right answer of 5 times 4 all the way on to 1. So let's run this, and bam, the answer is 120. And just to prove to you that that is really the factorial, just in case you don't believe it, hey, look at that. Okay, so that is the answer, and now let me show you why. Okay, if you don't really trust this like let's just pray that this smaller recursive call actually does the right thing. Let me show you why it works using this magical idea of a stack diagram. Okay, so when we call, let's go back to blue, it's easier to read. When we call fact of 5, we have our program is trying to do some things, right? It needs to remember what it's doing. So we have this concept of a stack. So it's got to print. It knows that it needs to print. Let's see here. How do I want to say this? The very first call we make, like that Python is working on, is print fact of 5. So really, at the end of the day, it needs to compute fact of 5 so that it can print it. Okay. So the thing that it's waiting to do last is actually print. So that's the print function call. It's on the very bottom of this thing called the stack. Okay? And what's it printing? Well, it needs to print fact of 5. Okay? So that's the thing it needs to print. So we need to go off and compute that and remember to come back to print. That's the idea with the stack. Okay? So then we go and print is like, okay, I need to figure out what fact of 5 is. Let's call that function. Fact of 5 gets called. Okay, and so now we're trying to run the fact of 5 function. That's the key. Can I do that? Yeah. So now we're up here. N is 5. It's not 1, so we're not in the base case. And so we need to make a new variable called x. And we need to put in there whatever fact of 4 is, because that's fact of n minus 1. Because only once we've called fact of n minus 1 do we have an answer to give back. You see that? The answer that we can give back to print, to actually print the 120. It's not ready yet, because we still have to call fact of 4 before fact of 5 can return. Okay? I hope you see that. We have to do this before we can finish the fact of 5 call. All right, so that means fact of 4 gets called. And this is where the magic starts happening. And eventually we're going to get down to the very tippy top, where we get to fact of 1, which is the base case, and it's all going to unwind is the term. Okay, so we call fact of 4, and now we're sitting up here. Okay, fact of 5 was sitting right here called fact of 4, and now we're back here. We're at a different version of the same function. Okay, this one's running now, and this one's running at the same time. Okay, that's the key. Fact of 5 is sitting right here, and fact of 4 is now ready to start. Okay, and is 4 this time. It's not 1. Okay, we're going to continue. We're going to have to call ourselves again. We're going to have to call fact of 3, because we need to get an x, right? We need an x value. Whatever fact of 3 is, we need to compute that. So bam, we call fact of 3. And so I hope you see what's happening now. Fact of 5 is sitting right here. Fact of 4 is also sitting right here. It's waiting for fact of 3, and fact of 3 has started. Okay? And again, and in this case is 3, because we called fact with 3. And so it's not 1, so we have another recursive call that we need to make. Fact of 3 needs to ask, okay, because remember, it's always trying to be like, okay, 3 factorial equals 3 times 2 factorial. So it needs to figure out 2 factorial. That is the idea. So up here we go. Fact of 3 calls fact of 2, because again, it needs to put something in its x variable. Okay, that's the point. So yeah, fact of 2 happens, and all of these facts, they're not finished yet. None of them has returned. All of these functions are working right now. Print needs to call fact of 5. Fact of 5 needs work from fact of 4 before it's done. Fact of 4 needs work from fact of 3 to be done before it's done. And then fact of 2 needs work from eventually fact of 1 before it's done. Okay, I hope that makes sense. So this is a tricky topic, so please yell at me. Come to office hours if you have any questions at all. So fact of 2, again, n equals 2 this time. And, okay, not n equals 1. So it's going to finally call fact of 1. It needs 1 factorial before it can return its 2 times 1 factorial. Okay? That's the idea. And so, finally, fact of 1 gets called. We have fact of 2, 3, 4, and 5, they're all sitting on this same line. There are different versions of this same function running. They're all sitting right here. And now it's fact of 1's turn to be the life of the party and to bring us all home. Okay? So the idea is fact of 1, n equals 1 finally. Yeah, that's the base case. So we will return 1 now. Fact of 1 is like, all right, I know the answer. It's 1. And so it gives back that answer to fact of 2, who was waiting for it. Fact of 2 is waiting right here. See that? That is the key. So with that answer, I guess I can make this even smaller. Why not? With that answer, we're ready to finish. Okay? Fact_f1 is done with its work now. Okay? It gave back its answer, 1. Fact_f2 is waiting right here for that. Yeah? And so now it can store 1 in its x variable. It's like, yeah, I needed that. And so then it can multiply its 2 by that 1. You see that? 1 was the answer. So it gives back to whoever called it, who was waiting on the stack, 2 times 1, which is 2. Okay, and now fact_f2 is done with its work. Usually these get erased, but I'm just going to write slashes through them just to show you what's going on. And so again, fact_f3 was waiting for work to be done by fact_f2. It was waiting right here. And oh man, did it get an answer back from fact_f2? It got 2 back. So it'll store that in its x. Hello. And yeah, then it's ready. Then it's ready to return 3, because n was 3 for that call, times the 2 that we just got back. Okay, from the recursive call. This is called the recursive call. That's what you say when you're calling yourself. It's a recursive call. Okay, so this is about to return 3 times 2, fact_f3, which is 6. See that? And now it's done with its work. And now we're back executing code, working on fact_f4. Okay, who was waiting for fact_f3? Fact_f3 is done. It's waiting right here. I will put the answer that I just got back from fact_f3 in my x variable. Thank you very much. So it gets the 6. And now fact_f4 is ready to execute this line of code. It's now done with this. It's like, all right, I got back my answer from the fact_f3 call, and all right, I can multiply my 4 by that answer. Okay, 4 times 6, which is 24, right? Isn't that beautiful? So now finally we're at the original fact call. Okay, fact_f4 is done too now. We're at the original fact_f5 call, which was the first thing that we wanted to do. And I hope you see how it's computing the answer. Slowly but surely, it's going like top to bottom. Okay, so now we're ready for fact_f5 to finish. Because it was, again, waiting on this line, it needed to know fact_f4 so that it can multiply. So it's always 5 factorial equals 5 times 4 factorial. It needed to know this, and now it knows it. We got it back. Okay, so x stores the answer that we got back, 24. And now we can multiply, or fact_f5 notices, it's ready for this line. This one, the previous one is done. It can multiply its 5 by that 24, okay? Which is, that's the 100 and then 20. So 120 is what fact_f5 returns to whoever called it. And it was print. Print was what set this whole chain off, yeah? Print needed to know the answer of fact_f5 so that it could actually print that out. That was the whole point. Okay? So now we're ready. We're done. Print gets 120, and then, like on the little screen, it's like, okay, I'm ready to print that. I will print this number out to the screen. And now I'm done. And now the program's over, because there's nothing left on the stack of work to be done. Okay? That's the idea. It's like, think of the stack as a stack of work to be done. And who wants whose answer? Because it's always the person below you wants your answer. That's how it's going on. Okay? So that hopefully proves to you why factorial is working. They're all working together. You essentially get to assume that the smaller recursive call works because eventually you're going to get down to the base case. Okay? Eventually you're going to get down to the base case and it's going to build up the answer. Okay? So that's the example proof, which may still be a bit hand-wavy. That's factorial. We are done. And now let me prove to you a bit more mathematically why recursion works. Okay? So if you've taken a more advanced math class, you may have heard the concept called mathematical induction before. It's a very, very fun topic. And recursion is like mathematical induction done backwards, in a sense. Okay? So let me generalize what we were doing and call the problem that we're trying to solve with recursion, I'll just call it P, because we can call any problem P, right? It doesn't have to be factorial. We'll have some others in a second. So in order to solve some problem P with some number, like P of 5. It's the fifth P problem. The idea of recursion is, well, I need those two cases. I need that base case, I need that recursive case, okay? The base case tells me how to solve the smallest problem, okay? And so let's say that P0 is the smallest problem, and we can solve it immediately, okay? So that's part of the recursive answer. We need some smallest problem that we can immediately solve, okay? So that's one piece of the puzzle. And then the recursive case, let's think about mathematically what that's saying, okay? The idea of this recursive case here was, if only I knew the answer to the previous one, then I can give you the answer to my original problem. That's what it's trying to do. If only I knew the answer to 4 factorial, I can give you the answer to 5 factorial. It's very easy. I can just multiply a 5 there. And that's the key. The recursive case in math, it's an if-then kind of statement. It's an implication. It's like, okay, you give me P of some number n, I can give you the answer. If only I had this, I can give you the answer to one more, to a one bigger problem, P of n plus 1. That's the idea. That's why we were like, okay, if only I knew 4 factorial, I can immediately get to 5 factorial. That's the idea of the recursive case, okay? And so this is why recursion works, okay? It's because eventually you're kind of working your way back down, okay? You're getting to P of 0, and eventually you're building yourself up, okay? And this is why in recursion you can actually assume, you get to assume that the recursive case's smaller problem gets solved correctly, okay? It has to be smaller though, otherwise this doesn't work. Here's the idea. We were trying to solve 5 factorial. That was essentially P of 5, right? And here's how we can build it up from our base case and our recursive case. This is why it's always going to work. Because starting from the base case, P of 0, we assume we have that answer, I can use the recursive case rule for the rest of time. Just be like, okay, this is saying, if only I had P of n, I can give you P of n plus 1. Hey man, I got P of 0. Let's use this rule. Let's use your promise to give me P of 1. Because you're telling me, if only you had P of n, for any n, you can give me back P of n plus 1. Use my P of 0 to make the P of 1 that I need. And we can use this recursive case until the end of time to solve any sized problem. P of 1 can make P of 2, because you can use this rule, set n equal to 1, and give you the next biggest answer. P of 2 knows how to give you back P of 3 in the recursive case. Just use the recursive rule, plug in n equal 2. P of 3 can make P of 4, and P of 4 can make P of 5. And the idea with recursion is you start here, and you kind of work your way down, and then it builds itself back up from this base case and recursive case. Okay, that's the idea. Hopefully, with these two answers, this more of an example that may or may not generalize, and this mathematical example that totally generalizes, should hopefully prove to you that I can solve any problem of any size using these rules. Okay, starting at P of 0, using the recursive case to build up the bigger answer, the bigger answer, the bigger answer, just one at a time. Okay, that's why 5 needed to call 4, needed to call 3, needed to call 2, needed to call 1. Isn't that fun? Recursion is a very, very exciting topic. It's one of my favorite to teach. Okay, so that is why it works, and that was one example. Okay, that was factorial. There are more. Okay, let me show you a different one. Let me show you power. Okay. Dun dun dun. So let me try. Let's pick up a good number. Let's see. Should I do this one? Why not? 2.5 to the 5. Right. Take a second. I encourage you. I really encourage you. Take a second. Pause the video and see if you can figure out the recursive solution of this problem. Okay, how does 2.5 to the 5 have a smaller power computation inside of it? Think about it, okay? While I make sure that we're still recording. Yes. Okay. Do you have a good answer? So it's always about, well, just kind of spread it on out. What is 2.5 to the 5th power? Well, it's 2.5 times 2.5 times 2.5, right? Times 2.5 times 2.5. Do you see it now? Recursion is all about, remember, it's all about solving a problem in terms of smaller versions of itself. So if I'm telling you that power is recursive, you need to find a smaller power computation inside of the original one that you wanted the answer for, okay? Do you see it? There are a few, aren't there? Again, there's a few. So you got this one, it's probably the most obvious. That's 2.5 to the 4, right? I guess you could also do it this way, right? Either way, it's totally fine. And then inside of that, there's 2.5 to the 3, 2.5 squared, 2.5 to the 1, yeah? And now, our job as mathematicians / computer scientists is to generalize this, okay? How do we figure this out? What is the recursive case? That's usually the easier one. How does this generalize to any number to the power of any other number, right? So, here's the answer. Here's the idea. Any number n to the power m, okay, we have to use variables. We just got to get used to that. That's equal to, how do we generalize this? Which one's the 2.5? Which one's the 5? N and m, right? So that's equal to n, right? N times, what's this? Okay, what's 2.5 to the 4 generalized to n and m? It is n again to the power of what? M minus 1. Do you see that? That's the key. Okay, so that is our recursive case. Isn't that beautiful? So this is going to generically solve our problem of computing the power of one number to another, as long as this number happens to be an integer. That's one key thing that we need, okay? Because we got to do minus 1, okay? And eventually we want to get down to some base case. So let's figure out what the base case needs to be, because we always need to stop, okay? We can't do this forever, because then we would never get an answer, right? That would be essentially an infinite loop. So let's figure this out. 2.5 to the 5, okay, using the recursive case rule, that's 2.5 times 2.5 to the 4. Okay, using the recursive case rule for this one, 2.5 to the 4 is, this will help us determine when we need to stop. That's 2.5 times 2.5 to the 3, yeah? 2.5 to the 3, that's another power computation. We can use the recursive case again. That's 2.5 times 2.5 squared. And then 2.5 squared, well, what is that but 2.5 times 2.5 to the 1? What's 2.5 to the 1? That's 2.5 times 2.5 to the 0, right? Sure it is. Okay, what's 2.5 to the 0? That's 2.5 times 2.5 to the negative 1. Technically true. Okay, what's this one? That's 2.5 times, oops, put the dot in the wrong spot. 2.5 times 2.5 to the negative 2. Again, technically correct, but we're not really getting to an answer. This is just like doing nothing, right? This is just going to go on and on and on until the end of time. When should we stop? When is a good place to stop? Okay? And I think there are two good places. There's either this one, okay? It's either this one or this one, okay? Either of those is a good place to stop, because 2.5 to the 1, we can immediately say, yeah, the answer is 2.5, sure. But if we want to be extra generic to do everything as much as possible, let's use 2.5 to the 0 as our base case, because that answer is always 1. You can just be like, okay, cut off the rest of the computation. The answer is 1 here. We're done. That's the idea. That's where we can stop, okay? So our base case can be n to the 0, any n to the 0. What's that? That's defined to be 1, right? Equals 1. Okay? And so if we use these two rules, we can then make a recursive power function. Isn't that cool? All right. Are you ready? So, yeah, let's do this. Let us get started with power. Dun, dun, dun. So, again, this is what we're going to be implementing in code. Okay? And I really do encourage you to take a second, try it out yourself, try to get this into Python mode. All right? And then we'll do it together. All right. So it's going to be def pow, and it's going to take two parameters, right? It's going to take n and m, because we have two numbers. It's like, okay, we want one number to the power of another, so we need those two parameters, n and m, as variables. And then we need to do recursion, okay? And we always need to see if we're done. We always need to check first if we're in the base case, because otherwise we just keep doing this forever, right? So if we're in the base case, if m is equal to 0, then we know the answer. This is the base case. We know the answer immediately. Anything to the 0 power is always 1. Yeah? Otherwise, we're in the recursive case. And we don't quite know the answer yet, okay? All we know is that the answer is the original n. We can make another x variable if we want. It's the original n times the smaller power, n to the m minus 1. So that's pow in our Python, n to the m minus 1. Okay? That's the idea. See that? That's quite nice. And then we can do return n times x. But also, we never needed this variable, okay? We don't need the x variable up here, because really, we're just using it in the return statement. So we can just do that. Yeah? That's how we can do it. Return n times pow of n and m minus 1. Yeah? That's how we can translate these two things into code. All right, so now let's do, dun dun dun, moment of truth. Let's try printing out pow of 2.5 to the 5. Are you ready? So, 97.65625, apparently. Let's see if that's true. 2.5 to the power of 5. Hey, look at us. Isn't that cool? So this is, again, a recursive answer. We're using ourselves to compute ourselves, and we get to assume that this is going to give us the right answer because it will build it up properly. As long as we build it up properly, this smaller recursive call is going to work. Okay, we get to just believe in the magic of recursion, because eventually we're going to get down to the base case, and then the recursive case, if we do it right, we get to assume that we get p of n, and we just use that to build up the correct bigger answer each time. Okay, so I do encourage you to try drawing the stack diagram for this pow function. It will help you to understand why it's working properly. It's going to be very similar to fact again. Okay, so this is another wonderful, wonderful example of recursion. Hey. Okay, so that was power, and there are a lot of problems that are recursive. Some, like this Tower of Hanoi problem, is actually easiest to do with recursion, believe it or not. I'm sure most of you would want to use a loop for power and a loop for factorial instead, but recursion also gets it done, and sometimes the answer is a bit easier to get. Okay, so let me show you a nice, cute example of recursion that's used all the time. Okay, it makes some of the fastest algorithms for things like sorting. Okay, like if you want to sort a list of things, like let's go back to normal colors. If you want to sort this list, the fastest way to do it is to use what's called a divide and conquer algorithm. Okay, so yeah, the idea of a divide and conquer algorithm is that it's going to split things apart and then recursively solve those smaller parts. Okay, it's going to break a problem into equally sized subproblems. Usually it makes two. It splits them in half because we like the powers of 2 in computer science. So let's just put a 2 here to make it even. So the idea is, if you want to sort this, first we're going to split it up. This is a good way to do it. This is one of the fastest ways to sort this thing using recursion. 3092. And so now it's split it up into 2 smaller subproblems, like, okay, let's sort this and let's sort this. That's the idea, okay? And recursively, it will make those sorted. That's the idea. And then, let's see here. This will be 5, 6, 7, 8, right? And then this one will recursively become 0, 2, 3, 9. And then we can just build them back up. It's an easy thing to do, to be like, okay, let's put an arrow here, see which one's bigger or smaller. And okay, the 0 wins, so we're going to move this arrow. Okay, now it's 2 and 5 competing. Okay, 2 wins. And so it's very fast to do this, to merge these all together, and it's actually called merge sort, this process. And that'll make your sorted list. Okay, so this is divide and conquer, and recursion gives us the answer. The magic of recursion. Okay, this is not something I'm going to test you on, it's just a fun little example. So yeah, usually the factor for divide and conquer is 2, but sometimes like you can split up a problem into 3s. That's totally fine. Why not? Sometimes it's easier that way. And then you can like recursively solve those, and then build up the answer, the final answer again. Okay, so probably a more simple idea is let's make a divide and conquer algorithm to add up all the elements of a list. Okay, why not? So we can take this one, and here's the idea. Here's the recursive idea. Dun dun dun. Again, I wouldn't dream of testing you on something like this. Recursion is a hard topic, but something like divide and conquer, that is. So just let this soak in, okay? It's good to know. All right, so here's what we want to do. We want to add all of the elements of a list together, and I want to show you that we can do this by dividing and conquering that list, okay? Dividing and conquering, and yeah, that involves splitting it up. Okay, so again, maybe we can start with this first list. We want to sum all the elements. Okay, I'm sure you know how to do this with a normal loop, but let's do it with recursion. So the idea is we want to split this list up into 2 halves. Okay, so we got a half, we got a half. And we want to recursively sum each of these, which is, I don't know, 1326, and recursively sum this one, that's 1114, and then we can just add together the answers. Okay, this is going to be the recursive case. So that's, what, 3040, apparently? Cool. And then we need base cases. So when do we have the smallest list that we don't need to divide and conquer anymore? There's no way to divide it anyway. If we have a list with just 1 number in it, the sum of all the elements, well, that's just 1. Yeah? Just that number that was there. And if we have an empty list that we want to sum together, all the elements, that's always 0, right? There's nothing there. Okay? So with this in mind, let me walk you through how I might implement this. Okay? Again, this is a very complicated example, so I'm not going to ask you anything like this divide and conquer example on any test. Okay? So here's the idea. Let's do def sum divide and conquer. So it's going to take a list, and for reasons, we're going to need to know, like, I think, or you know what? I don't think we need that. I changed my mind. We'll just take the list itself, okay? We're going to sum, divide, and conquer this list, all right? So I'll show you a trick with lists. Just split them up, split them into smaller things. So, like always, we need to figure out if we're in the base case or the recursive case. The recursive case involves the splitting. The base cases can immediately give back an answer, and these have to do with the length of the list. Do you see that? So let's take care of the base cases. Let's do the base case 1, and that happens if the length of the list L is equal to, let's do 0 first, okay? Then the sum is always 0. Yeah? Sum of all the numbers of an empty list, definitely 0. And now, let's say, okay, the other possibility is the length of L is equal to exactly 1. Okay? This is base case 2. And the sum of all the numbers in this size 1 list, it's, well, just give back that 1 number that's in there. Return L of 0. See that? Because remember, all the indices start at 0. Bam. And then else. Else, this is finally the recursive case, and this is where fancy stuff needs to happen. So we're going to divide. Divide so that we can conquer, okay? First, we need to divide the list into 2 halves. Now let me show you how we can do that. Okay? That's a neat little trick in Python. of working with lists. So let me make a list 1, 2, 3, 4 right here. So my list is called L, and if I want just the first 2, here's what I can do. I can say, L, please give me all the indices between 0 and not up to 1, though. Okay? So it's always 2 minus 1, just like for the range. And so then it's going to give me back the 1, 2 into a list. Okay, it's like this colon. It's like go from index 0 to right up until index 2. Yeah? That's the idea. And I can also get the other 2 by saying, okay, L, please start at index 2, and then go to the very end of the list, which can be, what's the index there? Well, 1 past it is length of L, if I wanted to do that. But there's shorthand for both of these. Shorthand for this is just say 2 colon. It's like 2 dot dot dot. Take everything starting at index 2 till the end. That's the 3, 4. And similarly, if you want to start at 0, you can say L just colon 2. Take everything right up until index 2. Okay? So what I want to do now is split it. How do I find this 2 from this length 4? Just divide it by 2. Okay? What's the mid? What's the midpoint? That is len of L over 2. And I want to use 2 slashes here because sometimes a list might be of size 3. And 3 divided by 2, that's 1.5. That'll never work. So this kind of like shrinks it down to the closest number, just chopping off the decimal places. So this is doing integer division. That gives me the midpoint, and I can use that to get the first half and the second half. Okay. The first half is L from colon to midpoint, and then the second half is L from midpoint to colon to the end. Okay. That's the idea. Now I have the 2 halves. Let's conquer them now. Okay, that's the idea. So, and remember what we're trying to do. We're trying to solve this sum problem. So conquering them recursively, this answer should always be a number. It's going to be the sum of the first half, the sum of the second half. Okay? Equals sum, divide, and conquer of first half. Okay? Let's make this bigger now. So here I am conquering the first half. I'm calling myself on this smaller list. So eventually it's going to give back the answer. That is the sum of the smaller list, the first half. Okay? And then we will do second half sum. Just replace first with second everywhere. And so now this will give me the answer to the sum of the second half. Okay? And then the final answer is, it's always the sum of both halves, right? How do we do that? How do we find that? Well, we have those answers, right? That's what the recursion gave us back. We have the 26 and the 14. All we have to do is add them. That's our final answer. Okay? Hopefully you see how this is working. I admit this is a difficult problem, so don't worry if it's not coming quickly to you, but I'd be happy to explain this in office hours if you'd like. Please yell at me. So the answer is just the first half sum plus the second half sum. And I'm too lazy to type it, so I'll do copy and paste. Okay? And this is going to work. This is eventually going to get smaller and smaller and smaller until it gets to the final answers. Okay? And maybe I can draw out what's happening. So yeah, let's test. Let's make sure it actually works first. Let's try calling this and printing out the answer. Let's sum 8s, 6, 7, 5, 3, 0, 9. Okay. Oh, and it was a 2 at the end, sorry, to make it even. It doesn't have to be even, though, because we have the 2 base cases for that. All right. I think that is good, so let's run it. And, hey, we get 40. Nice, 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 nice. Awesome. So, let me show you kind of why this is working, why like these double arrows actually lead to these answers. Okay? And that should hopefully drive it all home. Hey man, I wanted all of you. Oh man. Okay. Let's do this then. There we go. And we'll make a new slide, put it there. So here's what's really happening, okay? If you can believe me, if you can have the code next to you, it'll make it even easier to see. So the idea is this is still the recursive case, yeah? It's a list that's not size 0 or size 1, so it's going to split it in half, even, okay? It's going to split it in half. And so it'll make 8, 6. That's the first half. And 7, 5. That's the second half. And this will make 3, 0, and 9, 2. First half. Second half. And these are still non-size 0 or 1 lists, so it'll break those down to lists of just size 1 this time. We never get to a size 0 list with an even length, with a power of 2 sized list. This is 7, 5. And this is 3, the list with just 3, the list with just 0, the list with just 9, the list with just 2. And so here is where the base cases happen. And remember, these are always calls to, like, please sum this list. Okay, so this needs to give back the answer. And so all of these in the base cases are like, oh yeah, my answer is 8. Give that back. My answer is 6. My answer is 7. My answer is 5. My answer is 3, my answer is 0, my answer is 9, my answer is 2, and it's telling that to all these people who just called it, okay? To sum those smaller lists. So now 8, 6 is like, oh, okay, I have this answer and this answer, let me just sum those, and my answer is now 14. Yeah, and it gives that back to whoever called it. It's like there's arrows going back up for the unwinding of the recursion, okay? So this is kind of how I want you to think about it. And so the 7, 5, it'll make it 12, the 3, 0, that's like, okay, that's the sum. That's the sum I'm giving back now, the first half and the second half. My answer is that sum. My answer is 3. Gives back the 3. My answer is 11. I give back the 11. Okay? That's the whole point. And so now this one, again, its work is done. It's done its recursion. And so now it can solve its problems. Okay? It can be like, oh, I will solve the sum of 3 and 11. That is 14. The sum of 14 and 12. Oh, that's 26. And now the final answer, which was the call to this original size list, get its sum, please. That's the sum of these two sides. Okay? And so that's 40. And so it gives that back to whoever called it, like print. Okay? That's the idea. Hopefully this makes sense. That's a fun little example of what's called divide and conquer. And I think if we do this properly, this kind of like minimizes the number of additions we do, right? It's fewer additions than just like, okay, that one plus 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 that one. I may be crazy though, but divide and conquer is usually quite fast for what it's doing, especially for like sorting things. It's quite nice. So yeah, that is the end of recursion, and so we'll come back in the next lecture and talk about beautiful things, even though recursion was still beautiful, I think. That's why I lumped them together. So yeah, that is where I will leave you in this lecture. I will see you in the next one, and we will finish up these slides.